Okay, let's start with a number. A number that honestly gives me a little bit of anxiety. Tens of thousands.
That's a big number.
It is. That's how many code repositories a company like LinkedIn is trying to manage. We're not talking about some startup with one app. It's a digital metropolis.
It's a staggering scale, really. And when you're operating at that size, maintenance isn't the right word. It's more like urban planning.
Exactly. And today we're looking at a specific piece of that planning security, specifically static application security testing, or SAST.
Right.
LinkedIn just published this huge case study on InfoQ about how they completely overhauled their entire security pipeline. And I want to be clear right from the start, this isn't just about, here are the tools we bought.
No, not at all. This is an infrastructure story. It's about how you take a process that, let's be honest, usually makes developers miserable.
Oh, absolutely.
And you make it invisible, fast, and, well, scalable.
And it gets at a problem I think a lot of us have seen. You hear this term shift left. Everybody says it.
All the time.
We need to catch bugs early. Let's shift left. But in practice, what that usually means is you're just annoying your developers earlier in the process.
That is the cynical take, but it's often the accurate one.
Wow.
Shift left can just mean shifting the bottleneck to the pull request.
Right.
LinkedIn's whole mission here was to shift the detection left without shifting the pain left.
So let's paint the before picture. Because before this big project, LinkedIn was running what, I can only describe as a kind of Frankenstein setup.
Frankenstein is being generous. It was a completely fragmented ecosystem. You have to remember, LinkedIn grew so fast through acquisitions, through new features.
Yeah.
So over the years, different teams just spun up their own scanners. You had one team using this tool, another using that one, and some using, nothing at all.
So totally inconsistent coverage.
Wildly inconsistent. If you're the head of security, you have no single way to see what's actually secure. But the bigger issue, the real engineering problem, was the integration.
The plumbing.
The plumbing? All these separate tools were plugged into the pipeline in these ad hoc ways.
Which means what in practice?
It means traffic jams. You open a pull request and you're just waiting. Maybe 10 minutes, maybe an hour. And if the scan fails, the feedback is buried in some weird log file you have to go digging for.
I've been there.
Yeah.
You push code, you switch to something else, and an hour later you find out you missed a semicolon, and your whole flow is just dead in the water.
And that destroys your engineering culture.
Yeah.
If security tools are slow and the feedback is cryptic, developers will just find ways around them. Security becomes the department of no.
Yep.
LinkedIn realized that if they didn't fix the developer experience, the DX, then none of the security stuff would even matter.
So they decided to, just blow it all up and start over?
Pretty much. They came up with 4 guiding principles: developer first, extensibility, resilience, and observability. We can kind of skip the corporate speak, but the tech stack they chose is the interesting part.
Yep.
They didn't buy some all-in-one magic box. They went with a mix. They moved the whole orchestration layer into GitHub Actions.
Which makes sense. You meet the developers where they already are.
Exactly. No separate portals to log into. But for the actual scanning engines, the brains of the operation, they chose a combination of CodeQL and Semgrep.
Okay, I want to pause on that. Why 2? I feel like the trend is always consolidation. Why would you want to maintain 2 different scanning engines?
Because they solve fundamentally different problems from a computer science perspective.
Okay, break that down for me.
All right, let's start with Semgrep. Semgrep is what you'd call a syntactic scanner. It looks at the abstract syntax tree, the AST. Think of it like a really, really smart linter.
So it's looking for patterns.
Exactly. Simple patterns. Did you use this dangerous function? Did you hard code a password? It's incredibly fast because it doesn't need to compile the code or understand the entire program's logic.
So Semgrep is the speed demon. Good for quick checks, instant feedback.
Correct. But it's limited. It can't easily tell you if a piece of user input from your website eventually winds up in a database query 5 function calls deep.
Ah, okay.
That's where CodeQL comes in. CodeQL does semantic analysis. It builds a whole database of your code and lets you query it. It tracks what's called taint, basically, how potentially malicious data flows through your whole application.
That sounds computationally heavy.
It is. It's much slower than Semgrep, but it finds those really complex, deep vulnerabilities that a simple pattern matcher would just completely miss.
So, okay, Semgrep for breadth and speed, CodeQL for depth.
That's the whole strategy. Complementary coverage. If you only use CodeQL, every pull request would grind to a halt. If you only use Semgrep, you'd miss the really nasty injection attacks.
Got it. But, okay, you got these 2 engines. But here's the problem that always gets me. The output. CodeQL spits out one thing, Semgrep spits out another. As a developer, do I have to learn 2 different report formats now?
You would if they hadn't standardized on Serif.
SARIF, I've seen that acronym, yeah.
Yeah. Yep.
SARIF.
Static analysis results interchange format. It's basically a JSON standard. Think of it as the universal adapter for security tools.
Wow.
LinkedIn's pipeline forces both CodeQL and Semgrep to normalize their findings into this one serif format.
So the developer just sees security alert inside the GitHub pull request. They don't even care which tool found it.
They don't even need to know the tools exist. They just see a comment on the exact line of code that's broken, telling them exactly how to fix it. It makes the whole experience uniform.
Okay, this all sounds great in theory, but we have to talk about the elephant in the room, the architecture. Because setting this up for one repository is easy, 10 is fine, but tens of thousands, that's a logistical nightmare.
That is the scale problem. And honestly, this is where most big enterprise rollouts they fall apart. You can't just copy and paste a workflow file 20,000 times.
Well, you could, but good luck ever updating it. Imagine sending that email. Hey, everyone, please merge this tiny change into your 20,000 repos.
Exactly. You'd have what's called drift almost immediately. Some teams would merge it, some would ignore it. You'd have version 1 running over here, version 5 over there. A total mess.
So I know GitHub has a feature for this, required workflows. Why didn't they just use that?
They tried, but they hit some technical walls. At the time, and even now to some extent, required workflows have some limitations. But the big one was flexibility. If you force one single workflow on everyone and it breaks for just 1% of your teams, well, you've blocked 1% of the company.
Right. They needed something that could be managed from the center but still run locally.
Yes, and this is where they got really clever. The article calls it the stub workflow.
The stub work.
This is the magic trick. In every single one of those thousands of repositories, they placed one tiny file.
Oh.
A stub. It has almost no logic in it. It basically just says, hey, on a pull request, go call the central security workflow.
So it's just a pointer.
It's just a pointer. All the heavy lifting, the complex logic about when to run CodeQL versus Semgrep, how to parse the Sarif output, that all lives in one central repository that the security team manages.
So if the security team needs to add a new rule for some zero-day vulnerability, they update the central brain. And instantly, all 20,000 stubs are pointing to that new logic.
Instant propagation. No pull requests have to be sent out to all the individual repos. It's brilliant.
But wait, you still have to get that little stub file into all the repos in the first place. And you have to make sure some developer doesn't just delete it because it's annoying them.
Right, and that's where they built something called the drift management system. It's another automated process that just constantly scans the whole organization. If a new repo gets created, pop, the automator injects the stub.
And if someone deletes it,
it puts it right back.
It's like self-healing infrastructure.
That's the goal, yeah. It ensures that the contract between the security team and the developers is always enforced.
Okay, let's talk about that contract. Because we're now talking about blocking pull requests. This is where the rubber meets the road, when the developer hits merge and the system says, nope.
This is the enforcement piece. They use GitHub's built-in repository rule sets. If a scan finds a vulnerability that's, say, a critical or a high, the merge button is physically grayed out, disabled.
Which is great for security.
Yeah.
But it brings us right back to that developer friction problem. What if the scanner is wrong, a false positive? Or even worse, what if the scanner itself crashes?
And this is probably the most controversial part of their whole strategy, and I think the part that requires the most organizational courage. They chose to prioritize resilience over absolute security.
Resilience.
Right.
That sounds nice, but what does it mean in practice?
It means they designed the system to fail open.
Fail. Open. So if the security tool breaks, if GitHub Actions has an outage or the scanner just times out, the PR is allowed to merge anyway.
Right.
I know some security engineers whose heads would just explode hearing that. You're basically turning off the firewall because the fan is making a funny noise.
It sounds so dangerous, right? But think about the business logic. If you fail closed, if you block all merges until the tool is fixed, and GitHub Actions has an outage for 4 hours.
You've just halted all engineering for the entire company.
All of it. Thousands of engineers just sitting on their hands. That's millions of dollars in lost productivity.
And it completely erodes that trust we talked about. If I can't do my job because your tool is broken, I'm going to start hating your tool.
Exactly. So LinkedIn made a calculated bet. They decided the risk of one vulnerability slipping through during a temporary outage is lower than the guaranteed cost of stopping the entire business.
So how do they do that mechanically? How does the system know, okay, I'm broken, let this one pass?
They use that SARIF standard again. If the infrastructure detects a failure, a timeout, a crash, anything, it automatically injects an empty SARIF report into the check.
A fake report.
A valid report just with zero findings. It tells the GitHub rule set, hey, everything looks clean here, and the merge button turns green.
That is bold.
It is. But they don't just ignore it, they log everything. The telemetry captures that failure so the security team can go back later, fix the root cause, and maybe run a retroactive scan. But in that moment, the developer keeps moving.
It really hammers home that idea of security as a service, not a gatekeeper. If the service is down, the gate stays open.
It's a philosophy that, it treats developers like adults. It assumes most code being written is safe, and that blocking everyone for one system failure is a massive overreaction.
So we've got the tools, the stub architecture, the fail open policy. Now that this thing is up and running, what are they actually seeing? What's the payoff in terms of observability?
Because it's all centralized and standardized, they have metrics they could only dream of before. They can see scan execution times across the entire company. They can see which specific rules are causing the most failures.
So if one specific CodeQL rule is suddenly flagging 50% of all PRs, and they're all false positives, they can see that spike immediately.
And because of that central workflow, they can disable that one bad rule globally in seconds. In the old Frankenstein model, that rule would have just kept annoying developers for weeks until someone finally complained loud enough.
It moves security from this anecdotal, I feel like this is slow, to data-driven, this scan takes, on average, 4 minutes and 12 seconds.
Exactly, and it lets them track adoption. They know precisely which repositories are covered and which aren't. There are no more, dark corners in the city.
Before we wrap this up, I do want to clarify one thing. We've been focused on SAST, on scanning the source code.
Yeah.
But the article mentions this is just one piece of a bigger puzzle.
That's right. SAST is sort of the backbone, but the same pipeline architecture, the stub concept, it also supports dependency scanning.
Checking your open source libraries.
Right, for known bugs. And also secret detection to make sure nobody's committing API keys to the code. The stub idea works for all of them.
So if I'm a listener, maybe a DevOps lead or a CTO, and I want to, let's say, steal from LinkedIn's homework here, what are the key takeaways?
I think there are three big ones. First, centralize the logic, distribute the execution. That stub workflow pattern is just a brilliant way to get around the limitations of tools like GitHub Actions at scale.
It decouples the what from the where.
Perfectly put.
Yeah.
Second, standardize the output. Don't make your developers learn 5 different tool interfaces. Use SARIF. Normalize it all into one language so that feedback loop is fast and clean.
And the third.
Fail open. Or at least have a serious, grown-up conversation about it. Ask yourself, is our security tool so critical that it's worth stopping the entire company if it breaks? LinkedIn's answer was no.
That's the one that's going to stick with me. We tend to view security as this absolute, but at the end of the day, it's just another risk calculation.
Security is there to enable the business to run safely. It's not there to stop the business from running at all.
And that brings me to a final thought for you, for everyone listening. We talked about how LinkedIn designed their system to get out of the way when it fails. So as you look at your own pipelines, your own security policies, I want you to ask yourself this question. At what point does your security actually become a denial of service attack on your own team?
If you're blocking more valid work than you are actual threats, it's probably time to rethink your architecture.
Something to chew on. Thanks for the deep dive.
My pleasure.
We'll see you in the next one.